exponential and logarithmic functions. And today's lesson is kind of nice. Now we're mainly going to focus on exponential and logarithmic functions. Now we do have this little chart. It's not huge on the note sheet. It's kind of smaller. But we consider a function to be exponential, so b to the x, kind of that b to the x. Now we consider it exponential growth if that b, that value, is greater than 1. We call it exponential growth. And the way that we define exponential growth, or why we talk about it this way, well, we'll say 5 to the x. Now this is an exponential growth function. And if we look at the y values, because the x values for here, 1 through 10, are going by 1. But if we look at the y values, well, they start at 1, then go to 5, 25, 125, 625, 3,125, and by the time we get to 9, the number's gotten so big it doesn't even fit in that little box. That's why we call this exponential, because it's increasing exponentially. Because we could say 9 to the x. And its values are in red, and well, after we got 9 to the 7th, well, it got too big for the box. So they're increasing faster and faster rate. I have a feeling if we said 11 to the x, it's not even going to make it that far. Yeah, we can make it out to 5. 11 to the 5th is 161,051. They increase faster and faster. So, if the number is greater than 1, if this number, this base, is greater than 1, it's exponential growth. Questions on this here? Questions? Okay. Now, if that base value is between 0 and 1, we call it decay, exponential decay. So any number between 0 and 1, when it's written in this b to the x form, where b is between 0 and 1, it's exponential decay. Now, if we look at the first one, to tell whether each function represents exponential growth or exponential decay, and evaluate when x is 2. So our first one here, y equals 2 to the x. So our base in this case is 2. Is this value greater than 1? So that means that this one would be growth or decay. Growth. Because the base value of, which is 2, is greater than 1. Now it wants us to evaluate this for when x is 2. So we have 2 to the x. Well, we're going to replace that x value with 2. So we're saying 2 squared, which is 4. That's it. Questions on this here? Let's look at the next one. Y equals 1 over 2 to the x, 1 half to the x. Our base is 1 half. Is this base greater than 1 or between 0 and 1? It's between 0 and 1, yes. So would that be growth or decay? Decay. Yes. Now we want to evaluate this for when x is 2. So we're saying 1 half to the second power. Now we don't have to always do these by hand. We could have done the first one in the calculator. Because I could say 2 squared is 4. Or we can say 1 half squared is 1/4. Questions on A or B before we look at A and B? Be good with these so far. Now, if we look at the next one, 1.3 to the x. Our base is 1.3. So that tells us this would be growth or decay. Growth. And we know it's growth because our base, 1.3, is greater than 1. Yes. So now we're going to put it to the second power. The 1.3 squared is 1.69. Our next one, y equals 1/3 to the x. This would indeed be decay, because our base in this case is between 0 and 1, our 1/3. And since it's between 0 and 1, it is decay. And the last one, we're going to say y equals 1/3 squared, which is 1/9. We don't have to use just 2. I picked 2 at random when I put this together, just so we can see evaluations with it. Questions on this here? Are you ready for the next part? Oh, might as well go on and do these. We're going to determine if it's growth or decay. So if we look at number 1, 4 to the x, it would indeed be growth because our base is 4 and it's greater than 1. Number 2, y equals 2/3 to the x. So if it's growth, 2/3 is greater than 1, yes? And if we're not sure, we can always turn the fraction into a decimal. 0.6 repeated, so since that's less than 1, this is decay. Number 3, f of x equals 0.25 to the x. It is decay because 0.25, our base, is between 0 and 1. So it would be decay. And our last one, f of x equals 1.5 to the x. Growth, because 1.5 is greater than 1. Questions on any of this here? I feel good with this so far? All right, well, that wraps up 6.1. We're going to now look at 6.2. Okay, there's a few other things to it, but these are the main parts we're going to focus on. 6.2, so this here, history of mathematics, we do have something called E. E is our natural base for logarithms, and it has a specific value of this here, 2.71828182846. Now, it's an irrational number, so that decimal is non-repeating, non-terminating. It goes on forever like pi. Or not, yeah, it's irrational. So it's a non-repeating, non-terminating decimal. This here. Now, it's nice to know, not something you have to memorize or really know for sure, because the calculator can do it for us. It'll calculate it. But for the most part, E acts the exact same way as variables do. We can treat it almost like a variable. I did add 2 parts to the note sheets, because here, the first one, I'm going to write a similar example underneath, x to the 3rd times x to the 6th. What would x to the 3rd times x to the 6th be? X to the 9th, because when we multiply like bases, we add the exponents. Now, if we look back at the top, e to the 3rd times e to the 6th would be what? Huh? E to the 9th, yeah. Because we can treat it almost like a variable. So if that's true, if they act pretty much like variables, if we look at B, 16e to the 5th over 4e to the 5th, well, 16 over 4 is what? 4. Because 4 over 1 are just 4. E to the 5th over e to the 4th. When we divide like bases, we subtract the exponents. So 5 minus 4 is 1. And since it's bigger on top, it stays on top. So the next one is just 4e. C, 3e to the negative 4x squared. There's two ways we can do this. One is if we just are saying what it is, it's multiplied by itself. So we're saying 3e to the negative 4x is being multiplied by 3e to the negative 4x, multiplying it by itself. Well, our 3 times 3 would be, squared means what?
Oh, okay.
Yeah, squared means that it's being multiplied by itself. So we're really saying 3e to the negative 4 times 3e to the negative 4. Now you're good. Now we're multiply e to the negative 4 by e to the negative 4. Whenever we multiply like bases, we add the exponents. Well, negative 4x plus negative 4x is negative 8x. Now we're almost done. We can't leave an exponent negative. Can't leave an exponent negative. So if an exponent is negative, we move it from the numerator to the denominator, or denominator to the numerator. So here it would be 9 over e to the 8x. Well, helpful if I didn't go right over the top. Questions on C? Now we could have done this a little bit easier. Since there is one term, we don't have 3 plus e where there's not addition sign, we have to really write it out. We could square both terms. So if we square the 3, it'd be 3 squared. Now when we square a term with an exponent, we have our power of power properties. Because negative 4x is a power, 2 is a power, and our powers of powers multiply. Because we could say 3 squared times e to the negative 4x times 2. Well, 3 squared is 9. E to the negative 4x times 2. Well, negative 4x times 2 is negative 8x. And then we need to make the exponent positive, so we move it from the top of the fraction to the bottom. Questions on this here? Now, some of this is just having to go back and recall our power properties, exponent properties. Lastly, D. This one's not on your note sheet, so you'll need to fill it in. It'll be good to do these here. We can take these in parts. Square root of 16 is 4. And we're used to doing those sum. Now, variables with exponents. Well, as we just saw, powers of powers multiply. What do you think we would do with a radical and an exponent? We would divide. So we're going to divide our 4x by 2. And 4 divided by 2 is 2. We still have our x. So the square root of 16e to the 4x is 4e to the 2x. That's it. Let's look at the next 4. E to the 7th times e to the 4th is e to the 11th, because when the bases are the same, we add the exponent. So 7 plus 4 is 11. 24e to the 8th. So 3. Because 24 over 8, 24 divided by 8 is 3. E to the 8th over e to the 5th. When we divide like bases, we subtract the exponent. So 8 minus 5 is 3. Since it's bigger on top, it stays on top. Number 3, 10e to the negative 3x cubed. So we could write this out as 10e to the negative 3x, 3 times being multiplied together. Or since it's a single term, we can apply our exponent of 3 to both. So for our 10, we'd have 10 to the third times e to the negative 3x times 3. Well, 10 to the third is 1,000. E, negative 3x times 3 is negative 9x. But we do have to make that exponent positive. So we move it from the numerator to the denominator. Number 4. Yeah, I didn't have them on the note sheets. I put them on there an hour ago. Now, the cubed root of 64e to the 9x. Well, we need to take the cubed root of 64. A to the third is, let's look at, clear. Okay. Cubed root of 64 is 4. Yes. You're good. Because, yeah, 8 times 8, 8 squared would be 64. So we can take the cubed root of 64 in a calculator. It will do it for us. Now our exponent, e to the 9x, we can take the cubed root of it, but to do that, we divide the exponent by what? 3. So 9x divided by 3 is 3x. That'd be 4e to the 3x. Questions on this here? Last thing we want to look at is exponential growth and decay when the base is e. Now, when the base is e, we have e to the x. We're not so much looking at that value, we're looking at the exponent. Because if the exponent is positive, not the number in front of e, but the exponent itself is positive, it's growth. If the exponent attached to e is positive, it's growth. And if the exponent attached to e is negative, it is decay. So it's all about the sign in front of the exponent. If it's positive, it's growth. If it's negative, it's decay. Questions on this here? Now, if we look at the first one here, y equals 3e to the x. Would this be growth or decay? Because we're looking at the exponent, yes? Is this exponent positive or negative? It is positive, so it would indeed be growth. Now we're mainly looking at the e part, but e, because it's really e to the 1x, and well, e is 2.71 going on. So by our earlier definition, the base here is indeed greater than 1, yes? So it does hold true that this is growth. But because the base is e, it's an actual number, we're looking more at the exponent, it being positive or negative. B, here the exponent is negative, so it would indeed be decay. It would be a decay, exponential decay. Now, I'm going to do the same thing we just did, because we could say e to the negative 0.5 is 0.60653. Well, that number is indeed between 0 and 1, yes? So like the earlier definition, it is still decay. It still holds true. Let's look at number 4. The exponent is positive, so it is indeed growth. How about number 5? So the exponent, yes? Positive or negative? Negative, so it would be what? Decay, yeah, that's it. And the last one, the exponent is positive or negative? Positive, so it would be growth. It doesn't matter what numbers in the exponent are in front of it, because it could be negative 2x in the exponent, it's still decay. We ready for the next part? Homework. Now, problems 1 through 4, all you're doing is evaluating each expression for when x is negative 2 and 3. You're welcome. You're welcome. So there should be 2 answers on 1 through 4. 5 through 14. Determine whether each is exponential growth or exponential decay. So you're just saying growth or decay. You're welcome. On 15 through 18, simplify the expression, what we did with e, write it as a single term. And 19 through 24, tell whether the function represents exponential growth or decay. So you're just saying growth or decay. And that's it. Questions on any of this here?